Okay, so this question wants us to break down the meaning of the word dynamic. So in the context of a dynamic equilibrium, the dynamic part, remember dynamic means moving. So what's moving in here is the forward and backward reactions, and they happen at the same time. Absolutely crucial we get this point across. Okay, this second part of this question is a 6 marker, and there's a lot to this, but I'm going to help you hopefully to access it and break it down into different steps. So all I've done underneath is I've written out the equation that we were given, again, so you can see here, but I'm adding detailed the information from the passage of writing here. So it tells me in the forward reaction, it is endothermic. So endothermic, remember, means it's going to take heat in, and that means that the surroundings are going to become cooler. The opposite direction is going to be exothermic. Exothermic reactions give out heat. If they give out heat, then the surroundings are going to become hotter. So having this is going to really help me. Next bit of information is let's work out how many moles there are on each side. So here I've got propane. I've only got 1 mole of it. So on this side of the equation, I've got 1 mole. And on this side, you can see I've got 1 mole of propene and I've got 1 mole of hydrogen. So on this side, I have got 2 moles in total. So the question wants me to give the conditions that could be used to maximize the yield and rate of propene from the propane. So there's 2 parts to this. If we're talking about the yield of this reaction, then what I'm talking about here is equilibria, and I'm talking about Le Chatelier's principle, and I'm using the science of that to help me. If I'm talking about the rate, then rate, I'm looking at attainment, and I'm looking at rates of reaction knowledge. So it's 2 different aspects of knowledge that I've got to use here to bring together. So let's explore yield first and use Le Chatelier's principle. So I want to make more of the propene. So I want this reaction to move to the right-hand side. So the right-hand side is endothermic, making it cooler. So if I force this reaction to get hot, the reaction will try and make itself cooler. So it'll move to the right-hand side. So that's what I'm going to do. So in this first bit, let's break this question up. And this is how I'd present it in terms of little sections to help me think about it. So the yield, I'm going to say, let's increase the temperature. And if you increase the temperature, Le Chatelier says it is going to try and lower the temperature. To lower the temperature, the equilibrium shifts to the right, because the right hand side is endothermic. It's going to make it cooler, and that's going to lower the temperature. If it moves to the right, then I'm going to get more propene. So here, let's explain why though. So it's going to do that because the reaction is endothermic in this direction, and that's going to lead to an increase in the amount of propene, which is what we want. So that's a good thing to do. Pressure, we've got a difference in pressure. We've got 1 mole here and 2 moles here. So under normal conditions, this side is higher pressure. So what I'm trying to do is make this reaction move to the side that has higher pressure. How do I make it move to the high pressure side? Well, I lower the pressure, and that'll make it increase the pressure. So that's what I'm going to do. So the second condition to change is let's lower the pressure. If we lower the pressure, LCP, what does it say? It says it's going to try and increase the pressure. How's it going to increase the pressure? Well, the equilibrium will shift to the right. Why will it shift to the right? Because there are more moles on this side, and if it moves to the right, then the amount of propene is going to increase, which again is a good thing. So in terms of my yield, I've actually covered all aspects there. There's one bit I've going to come back to in a minute is catalyst, but we'll explain why I'm going to come back to that in a moment. Okay, let's think about rate. So rate, remember, is rates of reaction. This is trying to make particles collide. More collisions, more chances of successful collisions. The reaction is going to go faster. So one of the things that I can do is increase the temperature. If I increase the temperature, then this has a double impact on the rate, because the particles have got more energy. If the particles have got more energy, they will move more and there will be more collisions. And if there's more collisions, we'll get an increased rate of reaction. But before I write that, I'm going to add a little bit extra here. The other factor of this, there will also be more particles with energy greater than the activation energy. Remember, activation energy is the minimum amount of energy needed for particles to collide and react. So, if I got more particles with greater activation energy, there's going to be more chance of successful collisions. If they got moving around more, there's more chance of successful collisions. These two things lead to an increase in the rate of the reaction, which is what I want. I want that reaction, I want that attainment to be faster. The other thing that would cause that to happen is increase the pressure. If we increase the pressure, then what happens? There are more particles in a certain volume. And if there's more particles in a certain volume, that's going to lead to more collisions. And if there's more collisions, we'll get an increased rate of reaction. The reaction will go faster. Okay? But let's think about this. The yield that we just spoke about, it wants to have a low pressure. We've just said here that we would quite like to have high pressure. So we've got two different scenarios, one wanting one condition and the reaction wanting a completely opposite condition. What we have to do is we must compromise. We must find a pressure that's not too high, not too low, and that will work as best for this reaction. What we haven't talked about yet in detail is a catalyst. So catalyst, why are catalysts good? Well, what they do is speed up both the forward and backward reactions by the same amount. So catalyst will speed that up, and what that means is there's no effect on the equilibrium position. No effect on the equilibrium position, or the yield is how they're terming that. But what it does do is it speeds up the attainment, but will speed up attainment. So that reaction will be set up far faster. Okay, other things I would mention. Remember, you want to put as much detail as you can into these types of questions. So the other point is that we know that high temperature is good, but if using high temps, we have to be aware that in that situation, we would need to think about energy costs, because that is going to be linked to financial issues. So think about energy costs in terms of money. To get 6 marks on this question, all that detail is needed. So if you're not getting that detail into your response, you have to get the information in. I know you know this, But get the information in. Let's share the information so that other people know you know the information as well.